Hello, everyone. So another function that we often like to differentiate are exponential functions. So let's see how to differentiate those functions. So before we talk about exponential functions, there is one particular kind of exponential function that is somehow the nicest that we use most often, and that's the exponential function with base e, so functions that look like e to the x. So firstly, we should clarify what do we mean by e, and there are several different definitions. People pick the one that's most useful for them at a given moment in time, and they're all equivalent, but the one that we're going to use is that e is the number for which this limit equals 1. So if we look at e to the h minus 1 divided by h, and we take the limit, we get a number, and it's the number that makes this equal to 1. And okay, you might have seen this before, you might not have seen this before, but hopefully something you're aware of is that e is an irrational number, and it's approximately 2.7 something. Here it is to 5 decimal places, but I don't really count. So it's irrational, and for us, this is going to be our definition of e. So why should we do this? Well, the advantage of doing this is it makes the derivative of e to the x just e to the x. So that's one. I mean, there are many reasons to choose to be interested in e, but it makes differentiation very nice like this. What about with different bases? So if we have a different base b, then the derivative of b to the x would be b to the x times some logarithm of b. So for instance, the derivative of 2 to the x will be 2 to the x ln of 2. Derivative of 10 to the x will be 10 to the x ln of 10, and so on. So notice exponentials are quite different to powers that we saw before, right? So with exponentials, the base is a constant and the x is in the power. Whereas with the power rule that we saw last time and polynomials, the x is in the base and the power is a constant. So they're kind of swapped around. Okay, so now we can combine these rules with the rules we already saw for how to combine derivatives. So if we want to do the derivative of the sum, it would be the sum of the derivatives. So here, for instance, the derivative of 2 to the x becomes 2 to the x ln 2. Derivative of e to the x becomes e to the x. And then here, as I said, don't let this throw you off. Here, x is in the base, and e is just a number that's in the power. So this is just a polynomial or a power, right? So for this one, we would use the power rule. We'll get ex to the e minus 1. Okay, so just to say one more time, exponentials are when the base is a constant and the x is in the power. And for those, we use this rule. Okay, so let me at least modify why we have to use this definition of e. So why are we doing this? Let's suppose that f of x is e to the x, where a is defined as we had on the previous slide. And let's suppose we want to calculate the derivative. So why is the rule from the previous slide true? So what do we do whenever we want to calculate the derivative of something new that we've never seen before? Hopefully you're not going to have to do it too much, but we have to be able to do it. So we have to go back to the definition, right? We have to look at f of x plus h minus f of x divided by h, take the limit as h goes to 0. That's the definition of derivative. So let's try to do that. So we look at the difference quotient, and we replace f by whatever it is in this case. So f of x is e to the x, so f of x plus h becomes e to the x plus h, minus f of x becomes minus e to the x, we divide by h. And then we remember our rules for powers, right? So if we have a sum in the power, then it becomes, if we break it apart, it becomes multiplying. So e to the x plus h becomes e to the x times e to the h. I still have the minus e to the x. And then we notice that both of the factors both of the terms on the top contain an e to the x. So we can factor out an e to the x, we get e to the x times e to the h minus 1. Okay, so it becomes e to the x times e to the h minus 1 divided by h. And then the term involving h is exactly what we said should tend to 1 on the previous slide. Right, so if we take the limit as h goes to 0, this second term that we said on the previous slide goes to 1. This is going to 1, and we just get e to the x in the end. So we see that having this limit was exactly so that the derivative of e to the x would be e to the x. Okay, so now that we have that, let's use it to do some applications, do an example. So for instance, what point on this curve is the tangent line parallel to 3x minus y equals 5? So it's kind of an indirect question. We have to figure out what it's asking. So what does it mean for lines to be parallel? So the tangent line is going to be a line. 3x minus y equals 5 is going to be a line. We want to know when those lines are parallel. Well, they should be parallel when they have the same slope. So what we're trying to do is we're trying to figure out the point on the curve so that the tangent line has the same slope as this line 3x minus y equals 5. So let's try to figure out the slope of them both and make them equal. So the given line is, okay, we can rewrite it as y equals 3x minus 5. And remember, okay, if y equals mx plus b, then the slope is m. So in this case, the slope of the line we were given is going to be 3. Okay, now we're trying to find the point on the curve which has slope where the tangent line has slope equal to 3. So the slope of the curve at a general point x is just the derivative, it's dy dx. And now we can differentiate this using our exponential rules, right? So we differentiate the 1, that becomes 0. Derivative of a constant is 0. Differentiate 2e to the x, that's twice the derivative of e to the x, and the derivative of e to the x is just e to the x itself. So we get 2e to the x. And then we have to do minus 3 times the derivative of x. This becomes minus 3. For instance, with the power rule, or you can just remember that the derivative of x is 1. So dy dx is going to be 2e to the x minus 3. This is the slope of the tangent line at x. So we want to figure out what x value makes the slope of the tangent line equal to 3. So in other words, we have to solve 2e to the x minus 3 equals 3. So solving that gives us 2e to the x minus 3 equals 3, 2e to the x equals 6, e to the x equals 3. Okay, so x is the natural logarithm of 3. And since we were asked point, a point is specified by 2 coordinates, not only 1 coordinate. So we want to find the corresponding point on the curve to x equals natural logarithm of 3. So if x is logarithm of 3, then we find the y coordinate on the curve by subbing that back into the equation for the curve. So y was 1 plus 2e to the x minus 3x. We have to sub in x equals ln 3. So if we do that, okay, we have the 1, then we have 2e to the ln 3. Remember, exponential and natural logarithm are inverse functions. So if I do one and then the other, I get back to where I started. So here, 3 goes to ln 3, then I do exponential of that, it will go back to 3. So here I get 2 times 3, which is 6, minus 3 ln of 3, so I have 7 minus 3 ln of 3. Okay, so that's our point. So remember, points are specified by 2 coordinates. Okay, that's it for this time. So remember that the derivative of e to the x is e to the x. Derivative of b to the x is b to the x natural logarithm of b. And we can combine that with the rules we've seen before. Thanks. See you next time.